Hello, good morning. We're from HDR, presenting on how we used VISIM to model peak hour lanes using partial routes in VISIM. So with my colleagues, Jeshwan, Amini, my name's Matt. I'll just give you some quick project background. So this is on US 75. It's looking at peak hour technology lanes. It's kind of at the feasibility level. So just to get you oriented where this is, in the northeast area of the Dallas-Fort Worth Metroplex, US 75, about 18 centerline mile corridor from State Highway 121 on the north to I-635 on the south, hitting Dallas and some of the other large suburbs in that area, Richardson, Plano. The 2021 AEDT is about 212,000 vehicles per day, so a very heavily traveled corridor. So the goal of the project looked at mobility and safety impacts of converting the existing HOV lanes to peak hour technology lanes, and to provide short-term recommendations kind of the TSMO variety, such as there's quite a few separate merge diverge areas, so potentially connecting those with an auxiliary lane to create a weaving segment. So this is what our existing typical section looks like: 3 frontage road lanes in each direction, 4 general purpose lanes in each direction, and an HOV lane, 1 in each direction in the center, separated by pylons between the HOV and the general purpose lanes. And the HOV is 2+. And so this is what the potential proposed typical section is, basically converting that HOV lane to the peak hour or technology lanes. It's continuous access. Assuming we're as of now, assuming that the lanes will operate as HOV only, except during the peak period in the peak direction, where they will be sort of those designated peak hour or technology lanes. But however, this operations is still kind of under discussion with the client, with TxDOT and Federal Highways. So now, Ami, you'll kind of take us through the problem definition and some of the methodology.
Thank you, Matt. Moving on to the problem definition. US 95 is one of the top congested corridors as identified in Texas A&M Transportation Institute Mobility Report. Like Matt mentioned, it's currently an HOV lane with a limited access HOV lane, which is separated by pylons as with the GP lane extending from like 635 to Gallatin Parkway and Park Boulevard to Bethany Drive. Moving on to the future model, it's going to be a continuous access technology lane, which means like the users of the technology lane should register themselves in a GoKarma app, and HOV users of that lane will receive some incentives. However, like Matt mentioned, it's still under discussion, but for the purpose of the project, this was the scope we went with. So the goal is to attain maximum utilization and maintain a certain LOS in the technology lane, for which one of the assumption was to like, you know, in the peak direction, peak period, the lane will operate at capacity, for which the corresponding flow is 2,000 passenger car per hour per lane, and in the non-peak direction, it's an 1,800 passenger car per hour per lane. So the challenge is to attain this in the future model is that, like, since it's a continuous access technology lane, a managed lane facility or a managed lane routing decision approach was not a feasible way to go with. And we also considered separate routes for the same origin and destination. Since it's a continuous technology lane, and VISIM is link-based and not lane-based. So that was not another way to go with. But glad to know Vistra is already having a lane-based approach. Looking forward for that in VISIM. Moving on to the methodology, some of the assumptions that we had to consider and go with is we the foremost important thing is to identify which route qualifies into a technology lane route or not, for which we made use of future traffic projected balance volumes and existing street light data. This is just to understand, like, what's the OD pattern, and we assume it's going to be the similar OD pattern for the entire corridor, but out of which we had to filter out just the technology lane route, for which the technology lane, as you would see, like in the further coming slides, it's the leftmost lane in the corridor. So in case of a weaving section, it's going to be like it has to weave through 5 lanes, and in order to enter into a technology lane. So for which a conservative assumption of 1,000 foot per lane change distance was assumed, and for in order to for a vehicle to enter into a technology lane, it needs at least like a 5,000 foot to enter into technology lane. But like in a simulation, you could see, like, people might enter because of their aggressiveness or the speed curves. They would enter even further way ahead. And another similar approach was for the exit ramps, where they have to weave out at like 5,000 foot before the off ramp from the technology lane. And for those who know the corridor, like, the route, the 635 is itself a HOV lane. It gets connected to an HOV lane in 75. So the routes originating from 635, since they're already in the managed lane, they will qualify to be in the technology lane by themselves. So with this assumption in mind, an OD matrix was filtered out for the technology lane exclusively. So not all the inputs that qualify into the technology lane will be entering into the leftmost lane, but it has to satisfy flow and density criteria, which I spoke about in the previous slide, for which we extracted average speed, count, and length for the technology lane along all the lanes, and a weighted speed with respect to counts and weighted density with respect to length was calculated, and using which a flow was estimated for the segments. So the corridor itself has its own characteristics. Like southbound side is like the peak direction during the peak period, and the northbound has its directionality in the PM peak period. And the green box you see, like that's the area between 635 and PGPT. That is heavily congested as compared to the yellow box LS sections that you see, which is between Legacy Drive and 121. So in order to maintain the characteristic feature of the corridor itself, the entire corridor was split into 3 parts, and the weighted flow, density, and speed was estimated for these 3 segments separately. So to determine if a route qualifies into a technology lane or not, they have to meet this criteria. And since our intention is to maintain the LOS as well, so it is important to maintain this sweet spot. It has highlighted in the green box there, so as to fall on the left side of the curve and not move to the right side of the curve with increase in volume. And hence the flow has to be paired with the density. So in case of a peak direction, for at capacity LOS, it was 45 passenger car per mile per lane, and for non-peak direction, it's 35 passenger car per hour per lane. Sorry, yeah, per mile per lane. Now I'll pass it over to Jashwant for more fun part.
Thank you, Moni. Now moving on to the WISM modeling part of it, which is the core part of the presentation. Talking about the WISM modeling aspect, we have UDAs that we need to create. We have some partial route that we need to create. Before I dive deep into those things, I want to mention a disclaimer that ideally we would get our hands on the most latest features of WISM, utilize all the latest capabilities of it. But realistically, our project is limited to whatever we scope for or whatever the existing condition was calibrated to. So for our modeling purpose, we used the 2020 version, which had the latest feature of having the behavior of the lane based on lanes and not the links. So we incorporated that. But the latest feature, like Amani mentioned, like lane-based routing or the attribute modification that was talked about earlier, we're not able to be incorporated in this model. Moving on, we had to create a bunch of user-defined attributes for this project. So this is mainly because we had to create, we wanted to make sure we capture all the flow and density. In order to capture the flow and density, we had to create a bunch of user-defined attributes. And even to create those flow and density and speed user-defined attributes, we need to come up with a bunch of lane type attributes that we'll see in just a bit. So this one, it talks about the lane type user-defined attributes that we created. These are like lane link number, capturing the lane link number, capturing the lane link index, the number of lanes, the lane density. For those who attended Levi's presentation, these syntaxes might be similar. These are square brackets that we used inside the formulas, and those are just the formulas that we use to capture all the lane aspects of it. SNet is the UDA that we created to capture the speed of the network in the technology lane, corresponding to a specific direction or for a specific segment. For this, we tried to maintain a 2 decimal point result. So we used a floating point number in a vehicle and network object type. This is the sample formula for 3 links, but in our segment 18 mile long, there was like a huge link. We didn't want to put the whole formula in there, so we just put the template with 3 link over there, and we were able to incorporate the table lookup functions, all those vehicle attribute decisions, into this formula that you see here. Moving on, we have the density of the network. Like Amani mentioned, for the speed, we weighted averaged it based on the counts, and for the density, we weighted averaged it based on the link length, and we calculated the speed of the network for the technology lane and density of the network in the technology lane. And using both of those, we were able to calculate the flow of the network. Ideally, we would want to calculate flow without any of these hassle by just putting a maybe a data collection point, but since for this project, we wanted to calculate the speed, flow, and density at every timestamp, we had to come up with this workaround so that we can estimate at every timestamp and incorporate them in the formulas. Moving on to the partial routes that we had to create for this project, this section is going to talk about the approach that we use throughout the modeling and how the approach differs at the entering aspect, at the exiting aspect of the partial routes. This slide. So this is like the rough figure, which gives you an idea of how the methodology is going to be applied. The red route that you see is the bigger static route, which we calculated from the OD, and the nested partial routes are in green and pink color. So these are the partial routes that are going to be at the entering point and the exiting points. The green one is the entering partial route. So this is going to evaluate where exactly whether a route qualifies or not. So if I can point there. So if you see there's like 2 links, one that goes straight and one that is in a ring format. So when a vehicle enters the certain partial route, it gets evaluated based on the formula that we talked about before, and it sees whether it needs to go straight or pass through the loop. And that loop, what it does basically is gives the vehicle attribution, which pushes the vehicle into the technology lane, and the vehicle stays in the technology lane unless it's getting nullified at the exiting vehicle attribution. The exiting vehicle attribution is placed 5,000 feet upstream to the exit ramp. And we placed it 5,000 feet because, like Amani mentioned, it's going to be weaving out 5 lanes, and the assumption is 1,000 feet per lane. So we placed it there, and what it essentially does is check if the link sequence of the smaller partial route matches with the bigger static route, and if it does, it gets passed through the vehicle attribution and gets nullified. This is the Visual version of the exact same thing that we talked about. And you see the formula being different between the northbound and southbound. That's just because one is peak direction, one's non-peak direction, and 35 and 45 are corresponding to the densities, and 1,800 and 2,000 are corresponding to the flows. And the vehicle attribution, we had to be arbitrary, use the value of 10 for the desired lane because how wide the Texas roads are. If you use a 3 or 4, it might work for some segments, but it might not work for the majority of the segments. So we just assumed an arbitrary value of 10, which just pushes the vehicle to the innermost lane. And you see the vehicle attribution, the partial route, and the partial route is where the formula is being evaluated, and it judges whether a route qualifies for the technology lane or not. And similarly, we see the exiting partial route, and this is nothing but how we talked before, place 5,000 feet before the exit ramp, and yeah, it just sees if the static route matches the partial route. If it does, it goes through it and gets nullified. And once it nullified, it eventually comes to the exit ramp based on the lane change distance and emergency stop. And one thing you want to note is we place the vehicle attribution on all the links, all the lanes, and not just the technology. This is because sometimes when a vehicle is trying to get into the technology lane, it not always it makes it to the technology lane within the first 5,000 feet. In that case, what happens is sometimes the vehicle passes the point and then merges the technology lane and it doesn't get nullified. So it has to be passing through it. So we put it on every lane so that it get captured and get nullified, even if it didn't make it to the technology. Moving on to results. Here we talk about how we pulled some of the results and how we were able to manage to get the results that we wanted. Since most of the user-defined attributes were in vehicles and network format, we tried to get it through the vehicle record option that VISM has. The only problem that we had was since we had tens and thousands of vehicles at every timestamp, if we try to pull a vehicle record for the entire section, it's going to give us like a 1 gigabyte file for text file. We don't want that to happen. That's why we created like a dummy link with a dummy input where a vehicle just loops around, and we can just pull the result for that one vehicle, which gives a neat one-liner report for every 100 seconds. It's 100 seconds because the resolution is 1,000. And the dynamic labeling, like we talked about, like someone talked about yesterday, dynamic labeling is sometimes very important because you need to not wait for the end of the results. Sometimes we want to make decisions right when we like model and right when we view the simulation. So that's why we came up with the dynamic flow and density. And we created that such that vehicles get evaluated every timestamp, and we can see the results before it's like end of the simulation. Now we have the cool part, the VISM demo. We try to capture 2 good videos where we can see the approach, how it works and stuff. Hopefully it works. And you see the white car that passes through the partial route. It gets the vehicle attribution, but it does not get the blinker on. But the green car, when it passes through the vehicle attribution, since it qualifies on all the criteria, it gets the blinker on. So the criteria that I'm talking about is the 1800. Since it's the northbound in AM, it's 1800 passenger car per hour per lane, and the density is 35 passenger cars per mile per lane. So when it qualifies on those aspects, it gets into the technology lane eventually. And this is just a simplified version of what we just saw before. It's just one input, one output on the left and right. And if you notice, there's going to be a heavy vehicle which does not qualify. So it just stays on the general purpose, but all the other vehicles which qualifies gets into the technology lane. And similarly, we have the exiting where the vehicle passes through the vehicle attribution, gets nullified, and eventually leaves out. Moving on to conclusion, we have a bunch of graphs that shows how our results compared. So the top 2 graphs shows the results from the vehicle records that we pulled every 100 seconds, and the bottom result shows the data collection point that we put at 6 locations on all 3 segments. So if you look at these graphs, the top 2 graphs are averaged almost. The average values on the top one and the bottom one almost are the same. It almost at 1800 for the northbound and 2000 for the southbound. So one striking difference that we notice is that the segment 2 in the southbound AM is at a higher value. That's because when vehicles get determined whether they qualify for technology lane or not. Sometimes what happens is the vehicles which in their managed lane, like Amani mentioned, they automatically get qualified. So that's why we have a higher flow on the southbound AM. So apart from that, we see a common 1800 and 2000 that we wanted to maintain. So with that, I can take any questions. We can.